Hello everyone, I am Orel Lavie and my partner is Fidel, and today we are going to talk about a fascinating and innovative idea by Leo and Lejla, and also by Stjepan, our beloved guest lecturer from previous lecture on reversing neural network architecture via AM and SEA via deep learning. The paper is called One Trace is All It Takes. The paper describes how to attack an implementation of EdDSA in WolfSSL library on STM32F4 microcontroller, which is based on elliptic curve 25519 via convolutional neural network, CNN. The attack focuses on deleting information from the operation used to fetch the pre-computed result of the corresponding value of the elliptic curve scalar multiplication operation, which is based on radix 16 2 to the power of 4 algorithm to compute it efficiently in 4-bit nibbles instead of 256 bits all at once. If you tell yourself right now, what the heck he is talking about? At first glance, that was gibberish to us too. Do not worry, we will cover the details more thoroughly later on. As a glimpse, they showed that after CNN trained over 500 power traces, it predicted the nibble of the key with just one power trace. As a part of the research, they also compared CNN to other models such as plain template attacks and other machine learning-based algorithms such as SVM and random forest. Before we dive deep into our topic, let's cover the basics to ensure everyone is on the same page. Elliptic curve cryptography (ECC) is an approach to public key cryptography, encryption, DSA, key exchange, etc., based on the algebraic structure of elliptic curves over finite fields. The primary benefit promised by elliptic curve cryptography is a smaller key size, reducing storage and transmission requirements. For example, a 256-bit elliptic curve public key should provide comparable security to a 3072-bit RSA public key. ECC is based on elliptic curve discrete logarithm problem, ECDLP, which states that it is easy and hence efficient to compute Q equals K dot P, but it is difficult to find K knowing Q and P. You can think of it like the discrete logarithm problem which Diffie-Hellman is based on. This security is strengthened with a greater prime order of the underlying finite field. DSA and EdDSA. DSA stands for Digital Signature Algorithm. EdDSA stands for Edward Curve DSA, and it uses a variant of Schnorr signature based on twisted Edwards elliptic curves. EdDSA, when using parameters of curve 25519, is referred to as ED25519. EdDSA offers high performance while avoiding security problems that have surfaced in other digital signature schemes. This algorithm proposes a deterministic generation of the ephemeral key, different key, for every different message, to prevent flaws from a predictable random number generator. Curve 25519 is one of the twisted Edwards curves, a specific type of EC which was introduced by Daniel J. Bernstein. It is one of the fastest ECC curves and is not covered by any known patent. As a side note, to illustrate its importance, EC Diffie-Hellman, based on this curve, is the default key exchange mechanism in OpenSSH as of 2014. We are lucky today, as we just have 15 minutes to lecture, we can go over this complicated math quickly in a non-profound way. WolfSSL is a C language-based lightweight SSL TLS library targeted for embedding in RTOS environments, primarily because of its small size, speed, portability, and feature set. The implementation of ED25519 in WolfSSL is based on the work of Bernstein et al. STM32F4 is part of the STM32 family, 32-bit microcontroller integrated circuits, ARM-based architecture made by ST Microelectronics. In this paper, they use a Piñata board based on this microcontroller, which was made by Riscor. After we covered the basics, let's get deeper and talk about profiling attacks. Among all side-channel attacks, denoted SCAs, profiling attacks are the most powerful, where the attacker has access to a clone device with full control that can be profiled offline to later use this knowledge on another device during the attack phase. At the profile phase, we create a supervised dataset mapping from each trace to the respective subkey and use statistical analysis or ML and such to train. We could, in theory, get as many traces as we needed. At the attack phase, we use the model we train to predict. In this phase, we have access to much fewer traces, around 1 or 2. The types of profiling attacks generally divided into two families. 1. Template attacks, a type of profiling attack which assume Gaussian distribution and follow base statistical model to select a small number of points of interest, denoted POI, in the power trace by looking for peaks in a plot of difference of means. The second is machine learning-based methods, such as support vector machine, random forest, and such. As we mentioned earlier, the paper concentrated on CNN as its primary method, as a part of the ML family. Before we dive deep into the attack itself, we'll cover some related papers. Many common SCA countermeasures assume that the adversary needs access to multiple traces with identical scalar to recover the secret key, which inherently protects protocol with ephemeral scalars. Nascimento et al. In 2016 challenged this assumption and target fundamental building blocks of any ECC implementation, namely conditional moves and lows/stores from/to secret memory addresses. In the paper, they applied the horizontal attack on ECC implementation for AVR 80 mega microcontroller targeting the side channel leakage of CMOS operation, an operation that is at the very foundation of all scalar multiplication algorithms. There are essentially two different ways to implement this conditional move, CMOS, either by loading from or storing to addresses that depend on the secret scalar, or by using arithmetic operation to perform a conditional register-to-register move. They were able to recover 99.6% of the key bits for the arithmetic approach and 95.3% of the key bits for the approach based on secret addresses, with confidence levels 76.1% and 78.8% respectively. Their approach to side channel is similar to the one presented on our paper, but they don't use deep learning in the analysis. The second one is by Carbon et al. In 2019. This paper presents the result of several successful profile side channel attacks against a secure implementation of the RSA algorithm. The implementation was running on an ARM Core SC100 completed with a certified DAL for arithmetic coprocessor. This paper shows the high potential of deep learning attacks against secure implementation of RSA and raises the need for dedicated countermeasures. The first one focuses on the address indices manipulation, while the second one focuses on the operands manipulation. In both cases, the challenging point is to be able to successfully apply the attack to recover almost all the secret exponent bits by exploiting a single leakage trace after profiling. Gil will take it from here.
Thanks for the excellent intro, Orel, and now let's deep dive into the core of the paper. So, an attacker wants to forge signatures, so he needs to obtain the private key for signing. What does it mean exactly? Well, in our case, if we take a close look at the signature generation algorithm, we only need to get hold of the secret scalar A. There are multiple attack vectors to extract the value of A, but in our case, we'll do it by first recovering the ephemeral private key R, which is generated anew for each message signing operation. And then, if we have R, we can compute A, as we see in the formula in the bottom of the slide. So how are we going to extract an instance of the ephemeral key? Let's focus on the scalar multiplication operation. Capital R equals R times B. This is quite a computationally intensive operation, so WolfSSL has an optimized implementation of breaking R into 64 nibbles, 4 bits each, and using a pre-computed table of the partial multiplication results. For anyone familiar with side-channel attacks on AES, this should look quite similar to the S-box lookup which we exploited while attacking it. So, we have an ideal candidate for side-channel information leakage, namely, the pre-computed table lookup operation. WolfSSL is open source, so we can easily find where the table lookup takes place. See the calls to GESelect on the right? This is it. We're going to record power traces of the calls to GESelect by using the I/O pins of our evaluation board for triggering the power trace recordings. So we're going to start recording before the call to GESelect and then stop recording immediately afterwards, and that way we're going to have traces that record exactly the table lookup operation that we want to analyze. So let's take a look at the power measurement setup. So we have the scope and the power supply. Then there's the evaluation board by Rescure called Pinata that we're using for testing. So it has a connection for triggering to the scope to start recording, and also has a JTAG connection, probably connected to the computer over there. And on the bottom we see the current probe that's actually used for recording the power traces. Okay, now let's move to the digital board. So in order to evaluate the attacks, a dedicated dataset was created with a lot of power traces and the respective labels, each label representing the associated value of the ephemeral key nibble being used in the trace. The dataset is split with 80% of traces used for profiling, i.e. training, and the rest used for attacking or testing. It's also worth mentioning that the dataset is freely available on GitHub, and we actually use this later on. So, a number of different attacks were implemented and evaluated, namely template attacks, and the classical machine algorithms SVM and random forest, and finally convolutional neural nets. Each method was evaluated by first training it on the profiling dataset and then letting it predict the correct nibble of the ephemeral key given a single power trace from the test set. Testing was done with both the full 1000 sample traces and also traces pre-processed with PCA for dimensionality reduction. It's worth noting that extensive hyperparameter tuning using grid search was performed for the machine learning methods to get the best possible results. The CNN model used was inspired by the VDG architecture used for computer vision with some changes, the most major of which being the use of 1D instead of 2D convolutions to accommodate for the input being one-dimensional as opposed to two-dimensional images used for the original VGG architecture. So now let's see the results. And just like Chuck Norris here, I'll just say as a spoiler that the best results reported in the paper were obtained by a method that literally looks at the power traces. Can you guess which one is that? Okay, so here it is. The table on top shows the success rate for predicting the nibble from a single power trace, whereas the table on the bottom shows the success rate in getting the full ephemeral key from a single guess. This is basically the respective value from the first table raised to the power of 64, which is the number of nibbles needed to obtain the full key. We can see that the CNN-based method reaches perfect score when applied to the full traces, whereas for the dimensionality reduced traces, SVM and random forest actually perform better. And last, and in this case also least, template attacks actually also did not so bad. So after we saw that CNNs give a perfect accuracy when trained on the entire training set, it's also interesting to check what is the minimum amount of training data required to reach similar results. So it appears that as few as 30 traces per class, or a total of 480 traces, are actually enough to reach 100% accuracy, which is quite cool.
Since the dataset was available online, we decided to try and reproduce the results and also try evaluating the use of a fully connected neural network. It's notable that the authors of the paper actually shared some missing info about the hyperparameters of the CNN upon a request by email, and so thanks to them for that. We repeated the profiling phase 20 times for each method to account for inherent randomness in the training process to achieve more accurate results. So here's a summary of the hyperparameters we used for the evaluation. Nothing really interesting to see here. Moving on. But we did see some interesting results actually. So the CNN does perform slightly better than SVM and random forest, but a bit less than perfect accuracy in some of the repetitions. What's more interesting, however, is that SVM consistently achieves perfect accuracy except for a single test sample, specifically sample with index 936 in the dataset, on which it consistently fails in our runs. In our opinion, this calls for a more thorough examination and evaluation by creating a test set of at least 1 or 2 orders of magnitude larger in order to see whether this rogue sample is an outlier or maybe an inherent property of the problem space. Okay, let's wrap it up. We saw profiling attack against WolfSSL implementation of ED25519. We exploited the optimized implementation of the scalar multiplication operation using a pre-computed lookup table and were able to achieve remarkable results with a CNN-based profiling attack of 100% or near 100% attack success rate on a single trace after training on fewer than 500 power traces. In terms of future work, the authors mentioned that it might be very interesting to try the same approach of using the CNN against implementation that have some specific side channel attacks countermeasures. So it will be interesting to see if they succeed. This is it.